Hello everyone and welcome to PC Retro Tech. In this week's video I want to look at an old school demo effect called Raster Bars, and I'm going to be implementing it on this Amstrad PC1512, which is a PC clone with an 8086 processor running at 8 MHz. It also has CGA graphics. Now, I wouldn't normally do a video on a simple effect like Raster Bars because once you explain how they work there isn't very much more to say about them. But in this week's video there's quite a twist, as you'll see. Now I first need to explain what Raster Bars are, and in order to do that I'm going to use this tool which you can download for yourself, which is a lot of fun to play with, called the CGA Compatibility Tester. It's available on the oldschool.org website, and it was written by Trickster, who we've discussed before. He's certainly one of the world experts in PC demo effects on really early retro PC hardware. And if you download this tool, what it will do is run a battery of tests to check compatibility with the original IBM CGA implementation. So to run through all of the registers, all of the features, and even some of the undocumented features of the original IBM CGA card and see whether your card supports those features. So it's available on the website oldschool.org/PC/CGA Comp, or you can just search for CGA Compatibility Tester. But it won't run on more recent hardware. You really need very, very old PC hardware. It should run on a 286 without any problems, or anything earlier. And you'll need something that has some kind of CGA support, either full CGA compatibility or maybe just emulation. This is the CGA Compatibility Tester running, and as you can see it comes up with a menu of things that you can try out. Now I'm not going to go through all of these because I like to leave things in my videos for you to try out for yourself. But let's just take a look at the video RAM speed, for example. If I go to block memory write, it tells me that an original IBM CGA card will give 340 kilobytes per second of writes on a 4.77 megahertz IBM PC, but on this machine I'm getting 424 kilobytes per second, and that's because it's neither a PC nor is it an original CGA card. This is actually running at 8 megahertz and it's a Chipson Technologies card. Now the one that we're interested in here is M6845 compatibility. So 6845 is the chip that's used in the CGA card. It's actually used in a number of other video cards as well. And for example, if I go to vertical retrace, this will check that it can detect when vertical retrace is happening. And it tells me that it's 59.9 Hertz, which is exactly right for a CGA card. And the other option, one that we're really interested in, is horizontal retrace. And what this test does is display some raster bars, and the horizontal retrace bit is necessary to detect when you're at various rasters on the screen, so that you can know when to turn the raster bars on and off. So let's run this and see what happens, and as you can see, absolutely nothing. It just says that there should be some bars moving up and down, but there aren't. And that's because this particular chipset is not 100% CGA compatible. So let's try this now on an IBM PC and see what difference there is. So here we are on the IBM PC with a genuine IBM CGA card, and the same test now has 4 bars moving up and down the screen, and these are raster bars. Now the first thing you want to notice is that they run all the way from the right of the screen through to the left, including the overscan area where you normally can't display anything. And that's because the colours that you're seeing there are background colours, not foreground colours. And the second thing you might want to notice is that there are 4 colours here that aren't in the normal CGA colour palette. The green and brown are certainly part of one of the palettes. Those are foreground colours, but these are only displayable because they're background colours. Now normally you can only have one background colour and the whole screen is that colour. But there's a trick. If you can turn the background colour on and off fast enough and change it fast enough, then you can have it display for only a small portion of the screen. But you can't just turn it on at any old time. You have to wait until the electron beam has gotten to a certain point, and then change the background color and then change it back to black again once you get to the bottom of your raster bar. Now on old 8-bit machines this wasn't too hard to do because they often had raster interrupts, so you just basically program it to tell you when you get to a certain line, and then you turn the background color on, and then you program it again to tell you when you got to a different line, turn it back off again, and that would be your raster bar. On the IBM PC you can't do this because there are no raster interrupts. Instead you have to actually count rasters, and for that there's a bit that you can check in the 6845 chip which tells you when you're in horizontal retrace. So if you count those bits and count down a certain number of horizontal retraces, you can know which raster you're on. And so once you reach the right raster, then you change the background color. Now this is quite a lot of work because the CPU has to sit there polling the horizontal retrace bit and counting down to the right number. Now the problem is that there isn't very much time left to do anything else. So obviously you have to change colors if you want more than one color raster bar, and you have to compute the start and end positions of your raster bars, which are changing all the time. And you can't do this at whatever speed you like. You have to do everything at 60 frames per second, because if you don't change the color at exactly the right moment within a frame, then that entire frame will have colors displayed at the wrong time, and you'll just get an ugly flickery mess. So it requires incredibly tight assembly language and a lot of mathematical and bit twiddling trickery in order to do this. And raster bar implementations are usually measured by the complexity of the raster bars, how they look visually, and also by the number of raster bars that you get on the screen. And Trickster's really excelled here. He's got not 2, not 3, but 4 raster bars. They also interfere with one another as they cross over each other. And moreover, they're solid color raster bars, which are actually harder to do than other kinds of raster bars, as you'll see a little bit later. Now we come to the Amstrad PC1512, and if I run the same test on here, you can see that it does actually display raster bars, but if you take a look, they're all right at the bottom of the screen in the overscan area. This is really weird. It certainly says that the Amstrad PC1512 is not 6845 compliant, but why on earth are the raster bars right at the bottom? So this is a mystery that certainly needs to be solved. So let me show you how I went about figuring this out. The first thing to do is to ask Trickster himself, of course, but someone has already done that. John Elliott, who is actually active with the Amstrad PC1512, asked Trickster back in 2009, and you can see here in his results from this test, he says the retrace detect test, the bars are barely visible at the bottom of the screen. And that's exactly what we're observing. Trickster gave a very detailed response here. So first of all, he says, wow, the actual CGA card isn't even that slow, and it's even slower than the PC Junior's display memory. So this is actually an interesting fact, that the CGA implementation on the Amstrad PC1512 is about twice as slow as it is on other clones running at 8 MHz. And this is actually the reason that I got into this, so I'll come back to that a little bit later. So then there's another test that fails, and Trickster says, well, that's not a bug in my code, there must be something weird going on here. And then when John talks about the retrace detect test and the bars being at the bottom of the screen, Trickster says, that is also very surprising. I draw the bars by monitoring horizontal retrace, obviously, and I start drawing only after waiting for the start of the display cycle. The fact that the bars are at the bottom is very confusing. And I had a bit of a scroll through the rest of this thread and didn't find any additional answers. So at this point, it was both unknown and unexplained. So let's have a look at what the real reason is for this problem. This is the Amstrad PC Technical Reference Manual, which is available online, and it goes through the Amstrad PC1512 hardware and gives some technical details. So the segment that we're interested in is the VDU Status Register. VDU stands for Visual Display Unit, and it tells us that at port 3DA there is this register with 8 bits. So this is actually a 6845 register inside the CGA chip, and it's a standard register that's available in most CGA implementations. So the 2 bits that we're interested in are bits 3 and 0. So 3 is frame flyback time, and this is used to monitor for vertical retrace. Technically it doesn't actually trigger at vertical retrace, but at something called the frame flyback time, and this is at the beginning of the bottom border. So there are 262 rasters on a CGA screen, and only 200 of those are actually able to have pixels, foreground pixels displayed on them, and the rest are the bottom border and the top border. So this will tell you when it's starting at the beginning of the bottom border, and it says 16 scans before the end of the top border it'll switch off again. So you use that to monitor vertical retrace basically. In the IBM CGA reference manual, it tells us that this bit should be used for detecting when it's safe to write to the CGA memory. And this usually gets toggled on during horizontal retrace, or if you like, the horizontal flyback time. And on this machine, on the PC1512, it just says that it's a toggle bit. So what happens is every time you read this register, this bit toggles. So it has absolutely nothing to do with being safe to write to CGA memory, or to do with horizontal retrace. So you can't use this bit to detect horizontal retrace. And this is why the test fails in Trickster's benchmark, and the reason is because he toggles this bit when he reads to determine whether or not he's in vertical flyback, and so then this gets set, and then he toggles it again every time he checks for a horizontal retrace. I mean, that's basically toggled immediately, so he doesn't need to do any waiting or polling, and so that's why his raster bars are so small and only at the very, very bottom of the screen. So this is basically the problem, and so in order to do raster bars on the Amstrad PC1512, we'd have to come up with a new way of doing it. It's clearly not going to be possible using the standard technique of checking this bit here. How did I get into this whole caper? Well, I wasn't actually interested in raster bars or in horizontal retrace originally. In fact, I was just showing off a video from this channel on measuring the speed of CGA in various implementations on a private Facebook group for Amstrad PCs. And you remember in that video, if you've seen it, that I discovered that the Amstrad PC1512 is about twice as slow as other 8 MHz clones when it comes to reading and writing CGA memory. So I was interested in possibly finding a way to speed up writes, or maybe using the gaps between the writes to do something useful. And in the manual here you can see why those gaps occur. So it turns out that the CGA implementation in the Amstrad, and this was pointed out by someone in the Amstrad forum, is actually on an 8-bit bus, not the usual 16-bit CPU bus. And moreover, instead of being clocked at 8 MHz, it's only clocked at 4. And there are some really long wait states inserted because of this. So when you do an 8-bit memory write, then there are 4 wait states inserted, and by the time you add the rest of the bus cycle, it's a total of 8 wait states, or 8 processor cycles. And if you do a conversion between the 16-bit bus to the 8-bit bus, there's 12 wait states, and by the time you take in the rest of the bus cycle, it's actually 16 processor cycles. So this thing is really slow. There's also this section in the manual on display RAM overhead access, and it says that the number of wait states that can be inserted by the VDU, because the dot clock is running at a different synchronization than the CPU clock, varies from 12 wait states or 12 processor cycles up to 46. So this is really a long delay. And so I of course thought that maybe we could do something useful when these wait states occur, especially these really long ones. But then we noticed on the Amstrad forum that every 63.7 microseconds you'll get one of these 46 cycle wait states. And we began to wonder what could be happening every 63.7 microseconds. And when we did the computations, this turned out to be every 509.6 CPU cycles, and this is precisely the length of a horizontal raster in a CGA implementation. So it seems that for some reason the card is actually inserting a very long wait state at the end of every horizontal raster. So this was the first clue that led to the ability to do raster bars on the Amstrad PC1512. So my first idea was to try and find a way to fill these wait states, especially the very long 46 cycle one at the end of each raster, with other instructions to do something useful, for example drawing a picture on the screen. So the first thing that I did was to try and figure out how many 16-bit memory writes I can do per raster, and it turns out that I can do 7 of those. In other words, you can only write 14 bytes to the CGA card every raster. And then I decided to try and figure out how many no-ops I could insert between these writes. So some of the writes I could fit more no-ops between because there were more wait states in that gap, and others I would have fewer no-ops. And I finally realized that the longest of those gaps is surely the horizontal retrace period, that 46 cycle one. Now actually I could only find a combination that would allow me to fit 5 no-ops between 2 word writes, and that only equates to about 20 cycles. So a no-op is 3 cycles, but you also have a bus access of 4 cycles per no-op. So this is significantly less than the 46 that was promised, but at least it's something. And I realized that it must correspond to the horizontal retrace. And so that's how I figured out that I can actually detect when horizontal retrace occurs by finding the optimal pattern of memory writes and no-ops in between those writes. I can actually determine exactly when the horizontal retrace occurs. And so this was how I managed to figure out how to do raster bars on the Amstrad PC1512. The first thing to do was to replace some of those no-ops with instructions for changing the background color. So here I changed from blue to red shortly after the vertical flyback period starts. So this is actually inside the bottom border, and then I change it back to blue again at some other raster during the main part of the display. Now I don't know how well it'll show up on camera, but there's actually some flickering going backwards and forwards on this very last raster, and that's because I haven't quite got the pattern exactly right here. It is possible to do that and you can get this completely stable. But why does this work at all? And you can think of it like gears meshing together. If you had a really weird shaped gear with different size teeth on the gear, it would only mesh up one way. And if you have gears that do actually match up because they're the right shape, but they're out of sync, what's going to happen is there's going to be little delays when the teeth don't fit into the holes. And so they'll be out of sync for a while until finally a tooth matches up because it's the right size, and then from then on everything will be in sync. So you can see that I never quite get in sync here. It's very, very close, but this last little bit of the line here shows some flicker due to the fact that by this stage things are still a little bit out of sync. The next thing I did was to change the color every third raster. And the reason I wanted to do this is because it would give me much more information about where things were getting out of sync. And initially I would have lots and lots of flickering basically all over the screen. And as I got more and more close to optimal, the amount of flickering would be reduced to a small region on the side and then a smaller region and so on. Even now you'll occasionally notice a big flicker on the right hand side, and that's probably due to memory refresh or other things happening inside the machine that interfere with it. But overall, almost every single raster here is now exactly stable, and so this means that I knew that I had code that could, in theory at least, change the color every single raster if I wanted to. So I had a tooth pattern, if you like, of writes and stuff interspersed between that exactly matched up with the timings of the CGA card itself. So at this point I was really excited because I knew this meant that I could get a Raster Bar implementation working. The next thing I wanted to do was to introduce some movement, and so I introduced a frame counter, and then I used that so that every so many frames I would change the starting point of the colors that I was using, and this gives the appearance of the bars moving up the screen. Now the reason I couldn't go directly to a full Raster Bar implementation is that every time you remove a no-op or some other instruction and replace it with something else, you start to lose sync again because the timings go out. And so you have to readjust your code by inserting or removing other no-ops until you get back to sync. And this is really a tedious process, and very, very many times when I tried to do too big a jump between implementations, I would completely forget how to go back to a stable implementation. So I had to restart the process quite a few times until I started saving lots of versions that actually work that I could go back to. And then I had to make incremental changes that didn't change the code by very much until I got to a full Raster Bar implementation. This is the first implementation that looks like a Raster Bar. You can see there's a red bar moving up the screen. You'll also notice there's a little permanent black bar here that it seems to be passing under. And the reason for that is it actually takes a few rasters to stabilize the pattern of memory writes that I'm using to keep sync across the frame. The other thing is I need to do some control logic in here. For example, I need to detect the vertical flyback time, which happens around here. So it's not possible to completely get rid of this. It's not like an IBM PC where all you have to worry about is that you don't miss any horizontal retrace pulses. And in order to do that, all that's necessary is just make sure you don't do too much work so that you overrun the end of a raster. On this machine, I don't have horizontal sync pulses, and so I need to keep sync across the entire frame. And I'm doing that by doing all of these memory writes, which wouldn't normally be necessary. Now, one way that I could fill in this gap here is just to use more than the 262 rasters, so it goes on to the next frame and then fill these in. But the problem with that is that then I'm only doing things every 2 frames. It's going to take an extra frame per frame to do everything. And that would mean that every second frame was black instead of having a raster bar displayed, and that would give even more flicker than my camera could manage. So the other thing that I'm doing to speed things up here, it looks a lot faster than the other things that I've shown you, is I'm moving the raster bar up by 4 rasters at a time instead of 1, and I'm also doing updates to the position of the raster bar every frame. All of the demos so far have been running at 60 frames per second. Now, I mentioned that I'm using continuous memory writes that are just running all the time in order to get sync. They're like the teeth on our cogs that can only fit in when the CGA card says it's okay, and that's what we're using to keep sync. But if I'm doing memory writes, where are those? They would display pixels on the screen, right? And of course the Raster Bar itself is just the background color being changed. In fact, that's just a 6845 register that's being altered. So where are all the memory writes? Well, I'm actually just writing 0 into memory so that no pixels will display. And there's not really very much point in using those pixels for anything interesting, because you can only fill in about a quarter of the screen every frame with pixels. That's how slow the CGA memory is in this particular CGA implementation. In fact, you don't even quite get a quarter of a screen. And besides that, because there's memory writes happening continuously with very, very small gaps of only a few processor cycles between each, you don't have much time to do any computation. So figuring out what to display, what pixels you should put on the screen, you don't really have time to do that. At last we have our first raster bar, and I've shifted the beginning and ending positions so that it avoids this black bar that was displaying before. And of course now it's changing direction when it gets to each end of its position. Now this is something that you'd normally do with a conditional jump. You know, if the raster has reached such and such a position, then change direction. But you can't really do this, and there's two reasons for that. First of all, conditional jump instructions in assembly are just too expensive. They take too long and you can't fit them in. The other problem is that a conditional jump takes longer if the jump is taken than if it's not taken. And so we can't have things taking variable amounts of time if we're required to keep exact sync. So the way this is handled is with a bunch of logic instructions and bit twiddling. Basically you can use the result of the carry flag to set all the bits in a register to 1 and then XOR that with something, and only if the carry bit was set will that value appear in the computation. And all of that is constant time and can be interleaved between the write instructions. So it's a bit of a challenge to figure out how to fit it all in, but it is possible, and as you can see we now have a real raster bar moving up and down, which is quite similar to the ones that Trickster had. It's 16 pixels wide. That's because of the mathematics I'm using, and it's also only in a region 128 pixels wide, again because of the mathematics I'm using to do the computations. Well, what could be better than a raster bar? Well, two raster bars, of course. So here I have a yellow and red raster bar going in opposite directions. Unfortunately, unlike Trickster, I'm not going to get to 3 or 4 on this hardware, and there's a reason for that. So I wasn't personally able to find enough time between the write instructions that I'm doing to keep sync in order to do the mathematics for two raster bars going in opposite directions. So I'm not saying it's impossible, but it's certainly a challenge that's going to take me much more than the week that I've been spending on this. So the reason that it's only showing every second raster here is because if you were, for example, doing the yellow raster, every second raster it's checking not whether it's a yellow raster but whether it's the position for the red raster, and it says, well, no, it's not the position for the red raster, and so I therefore should have the black background instead of the red background. So only the rasters where it actually considers, is this a yellow raster, which is every second one, is it actually going to set a yellow color. So anyway, this looks a lot better, I think, than the single raster bar, despite the fact that it's not full. It actually gives it a little bit of texture, in fact, and it's still running at 60 frames per second and is still very fast. But I think we can go one better than this. No one said that you had to keep the color of a raster bar constant over its entire range of motion. So here I have a blue raster bar that changes into a red one as it passes under the yellow one. Now that might sound like an advanced technique, but actually it was almost all written already by accident. The turbo assembler that I'm using for the assembly language here has a limit on the size of a macro expansion, and so I wasn't able to macro expand 262 rasters worth of instructions. In fact, I'd already broken it down into two sets of, well, 128 actually, The reason is that some of the other rasters have to be handled separately for this region down here, as I've already mentioned. So basically the ones that deal with the rasters up here just use blue as the color, and the ones that deal with the rasters down here use red as a color. So not a very complicated trick at all. So this is basically as far as I'm going to take this trick. I think that there's a lot more that would be possible even on this very, very difficult hardware. But I'm going to leave that for other people. I always leave a challenge or something interesting for other people to work on, now that it's been demonstrated that this can be done. So that's all I have for this week. Thanks very much for watching the video, and I hope to see you in a later video. Bye.